Welcome to the first part of lecture 13 on graph theory. So, here is the content of this lecture. So, we will talk about two connected graphs. So, we know that a graph is k connected if there does not exist a set of k minus 1 vertices whose removal disconnects the graph. So, similarly, a graph is two connected if there does not exist one vertex whose removal disconnects the graph. So, in this lecture we will characterize two connected graphs. So, let me start with an example, maybe example of two connected graph maybe. This is not two connected. Okay, so you can see that if you remove this vertex from the graph will become disconnected. So, this is this graph G is obviously not two connected. Okay. So, you want to characterize when a graph is two connected. First we give a definition. Two paths from U to V are internally disjoint if they have no common internal vertex. So, we are introducing internally disjoint paths. Let me give an example using this graph, for example, maybe say this is my U and this is my V, and I call these vertices say x, y, z. Then between these two vertices I can see there are many paths, but U x v, this is one path and the other path is U y z v. So, these two paths are internally disjoint, right. Now, if I say this vertex is W and this is A B, you can see that you can't find internally disjoint paths between U and W. Okay. So, that is why this graph is not two connected, and here is the theorem which sort of characterize two connected graphs. Theorem 1932. So, it says that G is two connected if and only if for every pair UV in V, there exist internally disjoint UV path. In G. Well, so G is two connected if and only for every pair of vertices there exist internally disjoint UV paths. Now, this condition is not true for this graph, because I can see that there does not exist internally disjoint paths between U and W, because every path from U to W has go through this vertex V. So, you can't find internally disjoint paths between U and W. So, the graph G is not two connected. This is just an example to illustrate the meaning of this theorem. Let us prove this theorem. So, this part, that for every pair of vertices there exist internally disjoint paths, then the graph is two connected. Since for every pair UV belongs to V, G has internally disjoint UV paths. Deletion of one vertex cannot separate U from V. So, G is two connected. Since between U and V, for every pair, take a random pair U and V, and there are internally disjoint paths. So, these are the two internally disjoint paths P and Q. Then obviously, just deleting one vertex, you can't separate U and V, right. So, deletion of one vertex is not enough to disconnect the graph G. So, the graph is two connected. Well, next we will prove the other part, that suppose G is two connected, then we prove by induction on DUV. So, D is the distance between U and V. So, you take a pair of vertices which are at distance DUV and prove that they have internally disjoint paths. So, prove by induction on DUV that G has internally disjoint UV paths. Okay. So, what the idea here is that we start with a pair of vertices which are at distance 1, and then we will prove that there exist internally disjoint paths between u and v when u and v are at distance 1. And then we will assume that this is true for any pair of vertices which are at distance k minus 1, and then finally, we will prove that this is also true for any pair of vertices which are at distance k. So, first step is the basic step. When distance of you take a pair of vertices which are at distance 1, that means u and v is an edge basically, right. When this is 1, the graph g minus u v is connected. Why this is true? Because when the distance is 1, that means u and v is an edge in the graph, and now if you remove this edge from the graph, then the graph becomes g minus u v. This is connected because as k prime g is always greater than equal to k g, which is greater than equal to 2. So, the graph is 2 connected. So, the connectivity is at least is greater than or equal to 2, the vertex connectivity, and we know that the edge connectivity is always greater than equal to the vertex connectivity. So, the edge connectivity is greater than equal to 2. That means, by removing one edge from the graph, you can't make the graph disconnected. So, that is why g minus u v is connected. That means, there exists an internally disjoint u v path in g minus u v from the u v path formed by the edge u v. So, what we proved is that so u v is an edge at this moment because the distance is equal to 1, and if I remove this edge from the graph G, there is a path between u and v, right, because after removing the edge u v, the graphs still remain connected. That means, there is a path between u and v. So, in the graph G, there are two paths, one is this path and the other path is that the path obtained by this using the edge itself. So, we proved that when the distance between u and v is 1, there exist internally disjoint paths between u and v. Now, the induction step is that let distance between u and v be k, and we will prove that there exist internally disjoint paths between u and v when they are at distance k. Let w be the vertex before v on a shortest path from u to v. Okay. So, u and v are two vertices which are at distance k, and our final goal is to prove that there are two internally disjoint paths between u and v. So, at this moment what we are assuming is that, okay, suppose this is the shortest path between u and v, which is, that means the distance between u and v is k, and w be the vertex before v on the shortest path from u to v. So, that means the distance between u and w is equal to k minus 1, right. Now, by induction hypothesis, G has internally disjoint u w paths, because we have assumed that this is a proof by induction. So, we will assume that there are internally disjoint paths between a pair of vertices which are at distance k minus 1, and then we use this fact to prove that there are internally disjoint paths between a pair of vertices which are at distance k. Okay, so, by induction hypothesis, G has internally disjoint u w paths p and q. Okay. So, u and w, suppose this is, so they are at distance k minus 1. So, this is one path, say q, and the other path, this is one case I am considering, that other path between u and w, which is p, p contains v also. So, the path is the path p is this path basically, the path p is this path from u to w, and path q is this path. Okay, so, this is one case, this is the case 1 when v is part of this path. So, this is the vertices of the path p union the vertices of path q. So, in this case we can see easily that, so here you can see that v is a vertex in the path p. So, under case 1 we can say that there are internally disjoint paths between u and v. So, the one path is between u and v, one path is this one and the other path is this one. So, in this case we can say that under case 1, if v is in vertex set of P union vertex set of Q, then we can easily find internally disjoint UV paths in G. Now, the case 2 is that B is not a vertex on the path VP union VQ. Okay. So, this is the situation where U is here, W is here, and U and W are at distance k minus 1. So, there are internally disjoint paths between U and W. This is P, this is Q, and V is here. So, V is not on the path. Now, since G is 2 connected, by removing one vertex, say vertex W, you can't make the graph disconnected. So, G minus W is connected from the definition of 2 connected graph. 2 connected graph means you can't find a single vertex whose removal disconnect the graph. So, if you remove the vertex W from the graph will still remain connected. So, G minus W is connected and contains a UV path R. So, again there are two situations. If R avoids P or Q, we have two internally disjoint UV paths. Why this is true? Okay. So, G minus W is connected and contains a UV paths, and if R is this one, then clearly we have internally disjoint paths between U and V. One is this R itself and the other one is Q union WV. Now, suppose R avoids one of them, not both of them. Suppose R is like this, suppose R is like this. So, R intersects with P, then this is my R and then also I can have two internally disjoint UV paths. One is R, this R, and the other one is Q union W B. So, these are the two internally disjoint UV paths. So, this is the first case in terms of R, of course. The other one is R may share internal vertices with both P and Q. Okay. So, in this case, let me draw the figure again. So, U W V, the distance between U and W is k minus 1. So, by induction hypothesis there are two internally disjoint paths P and Q between U W. Now, since the graph is two connected, if you remove W from the graph still remain connected. That means, there is a path R between U and V, and that path share internal vertices with both P and Q. So, this is my R now. Right. Now, I have to, in this situation I have to find two internally disjoint paths between U and V. Let Z be the last vertex of R before V belonging to P union Q. Okay. So, that means Z is this vertex. Z be the last vertex of R before V belonging to P union Q. Now, what we do is that we need to get two internally disjoint paths. So, we get the two internally disjoint paths in this way. So, we combine U Z subpath of P with Z V subpath of R to obtain a path internally disjoint from Q union W V. So, what is the meaning of this one? So, I need to find under this situation I need to find two internally disjoint paths from between U and V. The one path is this path U Z subpath of P union Z V subpath of R. So, this Okay, I should draw in this way. So, basically this is one path, this is one path, and the other path is this path, and you can see that these two paths mean one, this green and the orange, these two paths are internally disjoint. So, what we have proved here is that when we took two vertices at distance k, so there are internally disjoint paths between those two vertices, assuming the induction hypothesis that there exist internally disjoint paths between two vertices which are at distance k minus 1. Okay. So, what we have proved is that a graph is too connected if and only if there exist internally disjoint paths between every pair of vertices. That is all. Thank you very much.